Hi there. Welcome to lecture 22 of Machine Learning from Data. And we are going to look at how all the good stuff that we learned in the foundations part of this course is going to apply to neural networks. Okay? And remember, I told you, you can never escape the foundations. They're going to be with us, no matter what we do. Okay, so basically we will address approximation versus generalization and how that surfaces in neural networks. And then we'll have to address overfitting. Okay, so regularization and a specific technique for, regularization called early stopping, which can be applied to any iterative algorithm. And lastly, we'll sort of address a little bit the second step of learning, which is how you get in-sample error small. So we'll talk a little bit about minimizing the in-sample error more efficiently. Basically, how do we beef up gradient descent? Because it turns out that fitting the data with neural networks is indeed a challenge because there are lots of local minima, and also, the computation is itself costly, it's challenging. So we need efficient algorithms to minimize the in-sample error. Okay, and there's a whole field of optimization that deals with such, what is called non-convex optimization. Obviously, we're not going to cover that whole field, but let's, dip our feet in a little bit here and there. Okay, now what did we do last time? Last time we addressed how do we fit, neural networks to data at a very basic level in some sense. Okay, so when you specify a neural network, you tell me what are the weights. Okay, and now given the weights, I can compute the output, h of x for any input x. Okay, and that's the forward propagation algorithm. Okay, and you start with x, and then you propagate forward to the output. Well, that becomes the output of layer 0, and then you propagate forward to the output of layer 1, and then the output of layer 2, and so on until you get to the output of layer L. Okay, and then that's the, that's h of x. Okay, now, of course, that you can compute the output once you have chosen the weights, all the weight matrices that are going into every layer. Okay, but when it comes to choosing those weight matrices, we need a principled way to choose them, and the natural way is to fit, the neural network to the data, i.e., choose the weights, choose all your weight matrices to minimize the in-sample. And that's non-trivial because minimizing the in-sample error involves computing a gradient. Okay, and how do we compute a gradient? How do we compute a derivative of a function that we haven't even mathematically specified? Because forward propagation, which allows us to compute h of x, is not a mathematical specification of h of x, it's an algorithmic, specification of h of x. I give you an algorithm to compute h of x, which is forward propagation. Okay, so we need to develop a sort of parallel algorithm that computes the gradient. Okay, and that's what backpropagation essentially did. So what we did last time was, we said, okay, so for a given set of weights and an input x, you have an error, and we can compute all the outputs at every layer, including the last layer, which gives us h of x. And what we're interested in now is how would the error E change if I change the weights a little bit. Let's say the weight matrix WL into one layer. And we derive this fundamental equation here. Okay, which is that the derivative of the error with respect to the weights is the output of the previous layer, okay, multiplied by a sensitivity that's specific to the layer into which the weights are going. Okay, this delta L. And the meat of the backpropagation algorithm is to give a dynamic program, a backwards flowing algorithm that starts by computing delta for the output layer and then goes backwards one by one and computes all the deltas. Okay, so that's the backpropagation algorithm. Now, it doesn't make sense for me to go into the details of any of these things because it's hard to realize, it's hard to follow, it's hard to sort of grasp in real time. Okay, so you need to read carefully now the derivation that we did last time, the text, and ultimately you're only going to learn it when you implement it. Then you will see the nuts and bolts of backpropagation working and gradient descent with neural networks working. Okay, but we took a small neural network. Okay, with our two input features, intensity and symmetry for digits, we took 10 nodes in the first hidden layer, and there was only one hidden layer. So this is a baby neural network, and look at the level of overfitting that we can accomplish. Fantastic. Okay, we need to address this at some point today. Okay. And I also showcased, gradient descent versus stochastic gradient descent. And here the goal is just to minimize the in-sample error. So step 2. So the picture on the bottom is step 1. We clearly have fit the data well, but forget about E out here. This is just a total overfit. Okay. And step 2, how do we get the in-sample error low? Well, there are many algorithms. Okay, so we're now, suggesting stochastic gradient descent in this picture, but we will see that there are even more powerful algorithms. Okay. And so the goal for today is to sort of look at approximation versus generalization, address overfitting, And then talk a little bit about, how we minimize the in-sample error more efficiently. Okay? Because, training big networks on lots of data is a computational challenge, A. And B, there are lots of local minima. Okay, so, how do we address some of these issues? Okay, and let's go to the board. Okay, so let's start by looking at approximation versus generalization. Now, when we discussed universal approximation, remember I told you don't need deep networks. Okay, in fact, a single hidden layer suffices, providing you give me as many nodes as I want in that single hidden layer. And what does each node in the hidden layer implement? It implements a perceptron. Okay, so let's focus the discussion, on the single hidden layer neural network. Even though in practice you may want to use deep networks with multiple hidden layers. Okay, so let me show you what a single hidden layer neural network looks like. Just this is a reminder. Okay, so you have your input X, okay, and you have your hidden layer nodes. Okay, so I'll put them in sort of red here. Okay, and so you have your augmented 1. Okay, and let us suppose that you have M. So you have M nodes in the hidden layer, okay, and your input has D dimensions. So this guy has D dimensions. Okay, and so there are actually D plus 1 vertices here with the augmented 1. So there's an augmented 1 here. Okay, and now I'll remind you, what does each of these hidden units, we call them hidden units, what do they do? They implement a perceptron. Okay. Each of these implements a perceptron. Okay. And we call this the weight matrix W1. Okay. And then we have a final layer perceptron. Okay, nice. So we have a final layer perceptron. Okay, which produces H of X. Okay, so this is the one hidden layer neural network, and the basic parameter that you get to control is M, the number of hidden units. Okay, now, we had that very precise systematic notation for the general neural network, which we need because you have many layers. Okay, but it's a little bit cumbersome to use all that notation for this simple, one hidden layer neural network. So let me simplify the notation, and we will call this perceptron, well, you define the perceptron by its weights, so we will, since this is hidden unit 1, we will call these weights V1, and these weights V2, and these weights V, and these weights V3, and so on, up to Vn. Okay, so what's coming out of here? Okay, what's coming out of here is essentially the sign. Okay, the theta is coming out. What's coming out of here is theta of Vi transpose. Okay, X. That's what's coming out of here. Okay, and then we'll call these weights W. So you have W0. So you have W0, W1, W2, and so on up to Wm. Okay, because you have m hidden units. Okay, and so what is H of X? Well, H of X takes each of the perceptron outputs, which is of the form, so you'll have V1 transpose X, V2 transpose X. So you'll have, theta of V1 transpose X, theta of V2 transpose X, theta of V3 transpose X, and so on, theta of Vm transpose X. Okay, nice. Okay, and what we're going to do is we're gonna multiply each of these by W1, W2, W3. That's what this perceptron does, Wm. Okay, add the W0 and add all these up and apply a function theta again. Okay, so the output H of X is equal to theta of W0 plus the sum from J equals 1 to M of theta of Vj transpose X. Okay, and so let us call this the neural network. We'll call it the neural network, although technically it's the single hidden layer neural network with m hidden units. So I'll just call this the neural network. Okay, nice. Now, just to show you the progression that we have gone through, let me compare this single hidden layer neural network with some of the other models that we have seen. Okay, so let's start with the linear model with the nonlinear transform phi. So linear model, linear model with phi of x, okay, which is equal to, which has an augmented 1, and then phi 1 of x, phi 2 of x, all the way to phi, remember we called it d tilde of x. But now let me imagine, just for comparison purposes, that d tilde is m. So we go into an m-dimensional space, phi m of x. Okay, so what was the linear model? Well, depending on what the type of problem was, regression versus logistic regression versus classification, we would change this theta into either sign, identity, or sigmoid. Okay, so I'll just write it as theta of W0 plus the sum from j equals 1 to m phi j of x. Okay, so that's the linear model with nonlinear transform phi. And now let me show you one more model that we have seen, which is the radial basis function network. The radial basis function network, RBF network. Okay, with kernel phi, and typically we use the Gaussian kernel. So with kernel phi. Okay, so let me write down what's that hypothesis that's computed h of x. Okay, so this is theta of W0 plus the sum. Okay, so now let's assume that we are doing the RBF network with m centers, so m bumps. So then we have the sum from j equals 1 to m. Okay, so this is here k equals m. Here z space dimension equals m. This is just to compare. Okay, so k equals m. We have phi of what? Okay, so here we're talking about h of x equals, and h of x equals, okay, phi of what? Okay, phi of x minus mu j over r, okay, and we had a magnitude here, okay, and we take the linear model, so wj, so we take the linear model, okay, with similarity features. So it's very similar to the linear model with the nonlinear feature transform. What was the difference with the RBF network? The features were specific features. They were similarity features, specifically the similarity between x and the center mu j. Okay. Now, when I write all these models, you should see a striking similarity. They're all basically a linear model. Okay. Sorry, I left out the WJ here. The WJ. They're all basically linear models. What do I mean by basically linear models? So here, we're implementing a linear model in the final layer. W's. Here we're implementing a linear model in the Z space. And again, I forgot the WJ. Okay. We're implementing a linear model in the Z space. W's. Okay. Here, we're implementing a linear model in a Z space in some sense. Okay, but this is a Z space, a very specific Z space where the features are similarity features. Similarities of the input x to some centers mu j. Okay? And so here, the function depends on what's your measure of similarity. Here, the function depends on what's your feature transform. Okay? And here, the function depends on what are your perceptrons being implemented here. Okay, the specific linear model. Okay, so these are very similar. And that's what I told you. The linear model is going to be there everywhere. Okay, but now let's pinpoint the fundamental differences. Okay, let's pinpoint the fundamental differences. Okay, so when we talked about, the linear model with the nonlinear feature transform, we were very emphatic. We said that you have to choose your feature transform phi before you see the data. Okay, so let's call this, the simplest situation. And we know that when you've picked your feature transform before you look at the data, we can apply the rigorous, E in to E out bound. Okay, so feature transform phi picked before looking at data. Okay, that's the nonlinear feature transform. Tell me what it is before you see the data. Let's look at the RBF network. Okay. Slightly more complicated. Okay, slightly more sophistication needed. Okay, because we don't know what the feature transform is. We don't know how to compute similarity features until you tell me the mu j's. And in principle, I can pick the mu j's to fit the data. Okay, so with respect to the w's, yes, it's a linear model, but it's nonlinear with respect to the mu j's. Now, what did we say when we talked about the RBF network? We said, you know what? Based on the philosophy behind how it was derived and the philosophy behind, we're placing bumps on the data in order to represent the data, we said that we can pick the mu j's, okay, in an unsupervised way to just be the centers of clusters that represent the data. Okay. So here we picked, let's call it the similarity features, i.e. mu j, in an unsupervised way to, represent the data. Okay. Represent meaning we're going to place bumps around the data, and we'll choose the bump centers in order to represent, where are the data points. Okay. And here, okay, what's the feature transform? What's the nonlinear feature transform? It's the nonlinear feature transform is given by these perceptrons that are implemented. Wow. Okay. The nonlinear feature transform is given by the perceptrons that are implemented. So here, we are mildly looking at the data, okay, in order to decide what's our feature transform. Here, the features, you can think of this guy here as, an analogous to phi j of x. Instead, it's theta of vj of x, vj times x. So this here is phi j. Okay, and we are going to optimize these weights by fitting them to the data using gradient descent and back propagation. Okay, so we are going to fit our features to the data in a very real way using both x and y. So here, fixed features, fixed feature transform. Here, mildly fit feature transform. Fit mildly because you only need to look at the x values in the data to pick bump centers. So mildly fit, okay. Fully fit features. Okay. So here, Vj are optimized to fit the data, okay, just like the W's. Okay. That means, okay, that our features that we are using in this linear model have been, intricately fit to the data. Features fit to the data. We are picking features based on looking at the data. Here, phi is picked before looking at the phi, i.e. the features, i.e. features. Okay. Now, at a very high level, that is the sophistication that the neural network brings. Okay. It allows us to fine-tune features to the data. No fine-tuning of features to the data. You pick your nonlinear transform ahead of time. Mild fine-tuning of features to the data. So you can see, least amount of fine-tuning of features, a little bit more, the more. Humongous power. And that's what we saw in that picture when I showed you the overfitting to the digits. You are allowing me to fit my features to the data. And then, okay, I'm going to use a linear model on top of that. But that power to fit the features to the data is a humongous power. Okay, and I'll put it in blue now. Humongous power. Okay, and let's investigate that humongous power. Okay, because we need to control it. Okay, so specifically. Okay, and now you can see, it's beyond the scope of this course to get into the analysis which derives these kind of results. But specifically, this neural network, okay, achieves E in is O of 1 over m for regression, O of 1 over square root of m for classification. Okay, so basically, what is this saying? Okay, that if you give me, so this is, on no matter how many data points you have. Okay, no matter how many data points you have. Now, this is assuming in some sense that there's no noise. If there's noise, you can't really escape from the noise. Okay, so as long as there's no noise. Okay. If there's noise, you've got the best you can do, which is related to the noise, then plus order of 1 over n. Okay, so this is regression, this is classification. What is it saying? What it's saying is that if you allow me to increase my number of hidden units, I will fit the data. I will do what? I will fit the data. Okay. And the rate at which my in-sample error is going to 0 can be quantified in terms of the power you give me. And this is a very powerful result. Okay, basically it says, put more hidden units, you'll fit the data. Okay, and that's related to, the fact that we get to fine-tune the features to the data. Now here, you give me more and more dimensional feature transform, okay, but as you give me more and more data, if you give me much more data than the number of dimensions I have, I may not be able to fit the data because I have to pick my feature transform before I look at the data. Okay, I have to pick my feature transform before I look at the data. And here, I'm only allowed to look at the x values in order to pick my feature transform, and that might not be sufficient. Even if you give me lots of x values, it may not be, I may not be able to fit the data with similarity features unless you give me m approximately equal to n or root n. Okay, if you give me lots of centers, then I can fit the data. Okay, and a similar result is going on here. If you give me m large enough, I can fit the data. Good. Okay. And no matter what the data size is, the data size is getting larger and larger and larger. Okay, so we have to now see how do we get the link from E into E out. So we have to, so this is the approximation capability. So this is the approximation capability of neural network. And this is just single hidden layer. Okay. So let's erase, and talk about, how do we rein this power in? How do we stop overfitting the data? We need to talk about, generalization. So this is approximation. Let's talk about generalization. Okay, so let's talk about the generalization properties now. We saw the approximation properties. Well, those are humongous. Okay, so generalization. Okay, of neural network. And just to remind you what we're talking about the single hidden layer neural network. Okay, so we have X. Okay, and then you implement a bunch of perceptrons to your hidden layer. So you have M perceptrons. Okay, and then an output. Okay, so this is what our network looks like. Okay, and here we have W, and here, we have all our perceptrons, V1, V2, up to Vm. So V1 is a perceptron, V2 is a perceptron, and so on. Okay, and the output, H of X, is equal to theta of W0 plus the sum over J equals 1 to M, Wj, theta of Vj transpose X. But it's useful to sort of also have that picture. Okay, and I'll just tell you the results. So if your activation functions are sine, so then you have the multi-layer perceptron. Okay, then the VC dimension we know is dVC for this network is O of M D, so M times D, okay, times log MD. Okay. So the logarithmic factor. Okay, so, and this is almost tight. In other words, there are, it's possible to show that the VC dimension, you can construct a set of inputs of size, roughly speaking, MD that can be shattered. So this is tight within, maybe we can get rid of that log factor. So basically, the VC dimension is the product of your number of perceptrons and the input dimension of your input space. Okay, and if you have the tan H, transforms, then the VC dimension is even higher. Okay, so we know that it is m d m plus d, so quadratic cubic. Okay. And you might wonder, well, why is it even higher with the tan H? Because the tan H, well, certainly the tan H can do anything that the multilayer perceptron can do, because by choosing the weights large enough, the hyperbolic tangent approximates sine. So any dichotomy that can be done with the multilayer perceptron can be done with tan H. So tan H is more powerful. Okay, and it turns out that we can quantify exactly how much more powerful. Okay, and it's beyond this. You can read about more details in more advanced text/courses. Okay, but now what does this say? So we know that E in is O of 1 over m. For regression, E in is O of 1 over root m for classification. And we know that E out is, let's take classification with the multilayer perceptron. Although it's hard to manipulate, we can just at least analyze. E out is less equal to E in. This is the VC error bar plus, order of dVC over n log n. Okay. Well, there's a square root here. Okay. So let's see. If we choose m is approximately equal to square root of n. Okay. Then what happens here? So this becomes order of 1 over n to the 1/4. So this is 1 over n to the 1/4. Okay, and what happens here? Well, you have root n over n. Forget about the log term. We're doing very approximate analysis. So you have root n over n square rooted. So this term here is also approximately 1 over n to the 1/4. So we can balance the error bar and the in-sample error. That's more or less the best that you can hope for. If you try to get this smaller, this will get larger and dominate. If you try to get this smaller, this will get larger and dominate. And since the out-of-sample error is the sum, it's best to balance the two. Okay. And what does this mean? This means that, assuming that you can get E out 0, otherwise there would be an E out star, the best you can do, let's say because of noise. Okay, whatever the optimal you can do. Okay, so in theory, I should say that there is also an E out star. Okay. I'm just imagining that, there's no noise, let's say. Okay. What is this saying? This is saying that E out basically goes to 0, or E out goes to E out star, providing you choose the number of hidden units appropriately. Oh, very powerful result. We saw that before with K nearest neighbor and RBF. Okay, so this is a classical property of non-parametric techniques, that you can get to optimal error, by choosing m suitably. Okay, but this is a parametric technique because you need to learn weights. In the nearest neighbor algorithm, there's no weights to learn. So this is sometimes called semi-parametric. Okay, so this tells you that E out basically goes to E out star, and so this is sometimes called a semi-parametric method. Okay, and so what basically this is saying is that even though you have huge power, you better control the number of hidden units carefully. One way is theoretically, but in practice nobody does it theoretically. What's another way that you can choose the number of hidden units? Okay, another way you can choose it is validation. Okay, so old friends coming back to revisit us. See, foundations, we will never escape the foundations. Okay, let me point out one more thing about this. And so it's worth I'll give a quick sketch of the intuition for this. Okay, it's worth sketching the intuition for this because look, what this is saying is that, the number of perceptrons, so each of these hidden units is implementing a perceptron. So we have m perceptrons and then another perceptron that combines them, that cascades them together. Okay? And so you can think of this as basically m hypothesis sets. M perceptrons are being implemented on the output, and instead of picking one of those hypotheses, you're cascading. Okay, and that means that you get m times d. Okay, log d. Okay, and in one of the homeworks you studied the situation where you take the union as opposed to the cascade, where you take the union of m hypothesis sets. Okay, each of VC dimension d. You showed that the VC dimension of the union is growing like d log m. Okay, here it's growing like d times m. Okay, so that's just to compare that cascade. That's just to show you that cascading is much more powerful than taking the uniform, than taking the union of hypothesis sets. Okay, so cascading, so union. So this is the union of m hypothesis sets, mh, with h's with VC dimension D, so each of these perceptrons has a VC dimension d plus 1 because they're all operating on a d plus 1 space. The union of M hypothesis sets with VC dimension d plus 1 has VC dimension order of d plus 1 log M. So go back and see the exercise that you did. And now that exercise is becoming relevant. Okay, so when you take the union, you increase the VC dimension logarithmically in the number of hypothesis sets. Here, you're increasing the VC dimension linearly in the number of hypothesis sets. So cascading the VC dimension is O of D times M product, i.e. linear, i.e. logarithmic. Okay. That's just to show you the power of cascading. Cascading is way more powerful than taking the union of hypothesis sets. So it's worth looking a little bit at, where is this power coming from? Where is this product? So let me, in some sense, let me basically derive this VC dimension for neural networks, okay? And, maybe we'll make it an advanced supplementary module. Okay, but let me give a quick derivation of this. Okay, so let's take a quick look at the power of cascading. So we're going to look at the VC dimension of cascading. I'll do it in a slightly general context. I'll do it quickly, okay? And, then we can apply it to get this product for the VC dimension. Okay, so the VC dimension of cascading, okay, and this is a quick look. And we're going to focus on classification. So we're going to cascade. You have hypothesis sets that do classification. We cascade them. We get a new hypothesis set. What's the VC dimension of this cascaded new hypothesis set? So let's focus on classification. It's also the easiest to analyze. Okay, so what's the scenario? So you have your input X. Then you have hypothesis sets H1, H2, up to HM. Okay. And what does it mean you have hypothesis sets? So each of these hidden nodes is going to implement a hypothesis set, just like each of these hidden nodes implements a perceptron. So each of those implements a perceptron. Okay, and so you feed in X here, and you might pick from here a hypothesis H1. Okay, you might pick from here a hypothesis H2. So that means that what comes out of here is H1 of X. Okay, so each of these is a hypothesis set. You pick from here HM, and then we combine them, we cascade them together with some other hypothesis set H sub C. Okay, so it means you pick from here a hypothesis H sub C, okay? And so what happens? So X, gets transformed into, once you pick hypotheses from each of these sets, gets transformed to H1 of X, H2 of X, okay? And so on, HM of X, okay? And then this gets transformed to HC of this. So H of X is equal to HC of this vector. H1 of X, H2 of X, and so on up to M of X. Okay, so this is the feature transform. You can think of this as I transformed X into a feature, and then I apply my combiner, my cascader hypothesis on that feature. Okay? And so, we might be interested in what's the number of dichotomies that this cascading setup can implement, given, let's say, the VC dimensions of each of the individual hypothesis sets. So let us assume that the VC dimensions are of this hypothesis set is D1, of this hypothesis set is D2, of this guy is DM, and of this guy is DC. So these are VC dimension of the hypothesis sets. Okay. And now to get the VC dimension of the complete cascade, we need to look at how many dichotomies can you implement on endpoints. So imagine that you have endpoints, x1, x2, x3, and so on up to xn. Okay. If you have picked a hypothesis from each set, then that's going to transform this guy into h1 of x1, h2 of x1, and so on, hm of x1. Okay. You can think of this as it transforms x1 to a vector. This guy is going to get transformed to h1 of x2, h2 of x2, and so on up to hm of x2. Okay, and so on up to h1 of xn, h2 of xn, and so on up to hm of xn. Okay, and now Okay, we're interested in how many dichotomies can you do. So how many dichotomies can you do on these n data points? Well, let me observe something. So let's look at this column here. Okay, so this column produces a classification of each of your data points. Okay, so this column is a dichotomy on each of these data points. So this is a dichotomy implemented by the hypothesis set H1. Okay, and because the VC dimension is D1, the number of possible columns here that we can get by choosing H1 appropriately, the number of possible columns we can get here is at most, okay, so the number of possible dichotomies is at most n to the D1. Okay, that's the definition of the VC dimension. Up to, we can make some assumptions that the D's are at least, let's say, 2 or 3. Okay, so you can go and think back. So basically, the VC dimension upper bounds the number of dichotomies you can implement on endpoints. Similarly, this column here is a dichotomy on the endpoints. Okay, that has been implemented by hypothesis set H2. So a dichotomy from H2, and so there are at most n to the D2 such dichotomies. And similarly, this last column here, there are at most at most n to the dm possible columns here. Okay. Now, if I change the column here, I get a different configuration of all these n transformed points. If I change the column here, I get a different configuration. If I change the column here, I get a different configuration for this collection of n transformed points. So how many different configurations are there for these n points that I can construct? Well, I can construct this column in at most this many ways, and this column in at most this many ways, this column in at most this many ways. So the total number of configurations you can think of this as the matrix, but the total number of configurations for these data points, so the total number of configurations, you can call this, if you want, Z1, this is Z2, and so on, this is Zn. The total number of configurations for Z1 up to Zn is at most n to the power D1 times n to the power D2 times and so on, is at most n to the power D1 plus D2 plus all the way to Dn. Okay. Now, what is a configuration of these points? So I can suitably choose my hypotheses, okay, and get from these x a particular configuration of these points. Okay, and now I'm going to apply HC on these points. That gives me a dichotomy on these points, and that dichotomy is a dichotomy on these points. Okay? And how many ways are there for me to dichotomize these points? Okay? There are at most n to the DC ways to dichotomize these points. N to the DC ways to dichotomize Z1 up to Zn, and that's because the VC dimension of this guy is D sub C. Okay? So for each configuration of these points, I can dichotomize in this many ways, and each of those dichotomies is a dichotomy on these x1 to xn. Okay. So that means that the total number of dichotomies I can implement on x1 to xn is the number of ways I can dichotomize a particular configuration times the number of possible configurations. So the number of dichotomies on x1 up to xn is at most n to the dc times this guy. Is at most n to the dc times n to this sum, which is n to the dc plus the sum from I equals 1 to m of di. Okay. And now I'll just claim a little lemma. Okay, so lemma, n to the d is less equal to 2 to the n if n is greater equal to something like 2 d log d. Okay, well, basically, if n is omega, let's call it is in omega of d log d. And so what does this say? This basically says that, here's d. Okay, here's d. And this basically says that if n is large enough, if n is larger than d log d, then the VC dimension, you cannot shatter all the dichotomies. You cannot implement all the dichotomies. You cannot shatter any n data points. Okay, and because m of n is at most this, and so the VC dimension is at most d log d. So the VC dimension is at most is in order of d log d, where d is the sum of the VC dimension, basically sum of di plus dc log the sum of di plus dc. Okay, and in this application, so the VC dimension of each of these individual hypotheses is d plus 1, and the VC dimension of this guy is m plus 1. So we have the sum of these d plus 1s m times, so that's m times d, okay, times the log of m times d. Okay, so that's the quick explanation of why cascading is so much more powerful. It results in a product, okay, for the VC dimension instead of, a logarithmic in m, which is what happens when you take the union. So cascading is way more powerful than the union. Okay, so we've studied the approximation generalization trade-off. Okay, and one way to control, overfitting is to choose m small enough, for example, with validation. And now let's discuss a couple of other quick tools, okay, tricks of the trade for controlling overfitting. Okay, so let's erase and talk about overfitting, specifically regularization, and then a technique that is quite useful with respect to training neural networks using gradient descent. And you can actually use this technique for any iterative algorithm that minimizes the in-sample error. And that's called early stopping. We're going to meet some of our old friends again. So remember regularization and validation, they apply to neural networks. Surprise, surprise, foundations are here. Okay, so on the left is the overfit, very simple 10 hidden unit neural network. Okay, and on the right I'm showing what happens when we use a little bit of weight decay. Remember we studied weight decay when we did regularization. So we defined the augmented error. E augmented is the in-sample error plus lambda W transpose, lambda over n, W transpose W. Well, in our case, that was when we did the linear models, you had just one perceptron. In our case, we have, matrices of weights. So in our case, we have W1, W2, and all the way up to WL. Okay, and so this is just the sum of the squares of the weights. So we can, equivalently compute E augmented is equal to the in-sample error plus the sum of the squares of the weights. So sum over I over L, so the layer I and J. So remember, each weight connects a previous layer node I to the layer L node J of WLIJ squared. So we sum all the weights. And if you take the gradient, so the gradient of E augmented is equal to the gradient of E in. Okay, so there's a lambda over n, which I left out, plus lambda over n, the gradient of the squares, okay, which is just, so if we take the derivative, let's take the derivative of the augmented error with some weight, WLIJ, it's the derivative of the in-sample error with respect to that weight, plus lambda over n. Now this guy is just twice the weight itself. Okay. And so what this means is that the gradient becomes the gradient plus twice the weights. Okay, and so the derivative of augmented error with respect to the weight matrix WL will be the derivative of the in-sample error with respect to WL plus lambda over n, 2 lambda over n, WL itself. Okay, these are just the weights. Okay. And so, the update is WL, and if you're doing stochastic gradient descent, then it's just the in-sample error on that data point. Okay, but the update for gradient descent is WL. It goes to WL minus the gradient, okay, DE in by DWL minus, so there's a shrinking term, 2 lambda over n WL. Okay, and you multiply all of this by your learning rate eta. Okay, so that's weight decay. Very simple to implement. You just, you get this gradient from back propagation, and this is just, an additional term that there's essentially no computation here. Okay. And on the right, I show you what happens with, weight decay parameter. The amount of weight decay, lambda is just equal to 0.01. Very small amount of lambda. Look, it gives you a very nice fit. Certainly not the overfitting you've got on the left. Okay. Let me show you another technique called early stopping, which applies in particular to neural networks, but anytime you're doing iterative optimization. I'm showing you the result of this technique, early stopping. It's an interesting technique that applies to neural networks, neural network training in particular, and you can use it whenever you do iterative training. So let's talk a little bit about early stopping. It's another form of regularization, but it results from an interesting view of what's going on when you train. Okay, so when you train, you start at some weights. Let me call those weights W0. Okay, and that's the collection of all your weights. So it's a very huge dimensional space, and you take one step of gradient descent. So you do one step of gradient descent. So you do a step of gradient descent. Okay, and that takes you to the weights. Let's call it W. Let's call this W of 0. So it takes you to the weights W of 1. Okay. Now, what's the idea behind gradient descent? The idea behind gradient descent is you're going to take a step and the gradient step, the negative gradient step, is the best step. Remember, we derived this. So the W1 is the best set of weights to go to among all the sets of weights that are inside the sphere of, this step size. So if I draw a sphere of this step size, then, these weights W1, okay, in some sense are optimizing. You're picking the best hypothesis in this set of weights. So you can think of this as a hypothesis set H1. Okay, nice. Okay, good. Now let's see what happens when I take my next step. Well, I'm starting here and I take my next gradient descent step. So let's say it takes me over here. Okay, again, why did I take that step? Because it was the gradient descent step. It was the best step to take of that size. So if you look at all the possible weights that are in that sphere of that size, well, these are the best weights to take. Okay, so these are the best weights to move to. Okay, and effectively, well, this is the best set of weights in this originally shaded set of weights, which you can think of, any set of weights is a baby hypothesis set. And now I move to the best among these weights that are now going to be shaded, in this fashion. Okay, so now I move to the best set of weights in that set. Okay, so in other words, this set of weights is better than this. Okay, and then that beats everything here. So this set of weights is the best in this union of hypothesis sets. Okay, so let me call this union of hypothesis sets. Now I've got a new bigger hypothesis set. Okay, let me call that H2. Okay, and what have I effectively done by taking 2 steps of gradient descent? I've effectively searched H2, this bigger hypothesis set, and gone to the best hypothesis. So now I take a next step. I take another step of gradient descent. Okay, and that effectively searches, the ball around that set of weights. Okay, so this was W2. And this is now W3, okay, and the ball of weights around that set. This is the best, so we've got a new winner. This is the best, so this beats this, this beats this, this beats this. This was the best in all of that, and this beats that, and this is the best in all of this. So this guy is the best in this new union hypothesis set. So if I define a new union hypothesis set as H3, so this guy is H3. Okay, then W3 is a hypothesis picked from H3 that is best. I've effectively explored H3. So you see, with each step of gradient descent, I'm effectively exploring bigger and bigger hypothesis sets. So H1 is a subset of H2, is a subset of H3, is a subset of H4, and so on. Okay? And these H's are indexed by iteration number. So if this has a DVC D1, then this is less equal to D2, this is less equal to D3, this is less equal to D4, and so on. Okay, so what's the picture that goes along with this? The picture that goes along with this is, if I plot iteration number T, okay, then I'm picking the best and best hypothesis set in hypothesis in larger and larger hypotheses. So the in-sample error will be going down. Okay, and that's no surprise because I'm minimizing the in-sample error. But effectively, at each step, I've searched a larger hypothesis set. So, what's the link between the in-sample error that I've currently gotten to and the out-of-sample error for the hypothesis set that I've searched up until that point? The penalty I better pay is, this VC penalty that depends on the D VC for iteration T, omega of DVC for iteration T. because I searched a larger hypothesis set. So this is sort of what's going on. Okay. And if I decide that I'm only going to, try hypotheses 1, 2, 3 up to 1,000, that means I'm trying I'm doing 1,000 iterations. And what will the E out be? It's the sum. We've seen this curve many times. This is the bound on E out. Okay. But now what this is saying is interesting. Okay. What this is saying is interesting. Don't train for 1,000,000 iterations, because that explores too many hypotheses set, the too larger hypothesis set. There's an optimal VC dimension. There's an optimal number of iterations to train for. Okay. What's going on here? If I imagine and typically what we do is we start at small weights. So if you imagine, I start at small weights, W0, okay, and the optimal weights that minimize the in-sample error, let me call that W star. If I train forever, I will get to W star. And so that's the minimum. And so there are contours of constant in-sample error. Okay. Okay. And what's happening is I'm moving from W0 to W star step by step iteratively by doing gradient descent. Okay. So I'm implementing some trajectory along this, set of contours. I'm going from my start point to the optimal. And what this picture says is that there's an optimal number of iterations which balances the in-sample error you've gotten to plus the error bar you have to pay for the size of the hypothesis set you have searched. So, and this optimal T star, okay, is basically stopping the training early. Saying don't train forever and go all the way here. Stop when you get to some point here, W of T star. Okay. Stop the training early. Early stopping. Okay. Now, if you look at this picture, effectively what it's doing, usually we start at small weights and you need to go to some larger weights in order to minimize the in-sample error. By stopping early, effectively we are putting you at a smaller set of weights. So there's a link to regularization. That's why I said it's a form of regularization, but we call it early stopping. Effectively we're saying don't, as you search more and more, effectively you've used a bigger and bigger hypothesis set and you shouldn't go too far, because then you start overfitting the data and your pain and your E out is increasing. Okay. So there's an optimal number of iterations to train for. Okay. Don't minimize E incompletely. Okay. Now, how do we pick this T star? Well, that's the problem. Okay. And so what we can do is we can set aside a validation set, our old friend validation coming to revisit us. Okay. And so we'll observe the training error going down on our training set, E train. Okay. And typically the validation error will sort of do something like that. Okay. And then that tells us, the validation error is telling is our sneak peek at the out of sample error. It's telling us that, you should stop training here, T star. Okay, and that's the left picture in the diagram there. So, and that's real data. That's the real digits data. Okay, no made up data, real algorithms running on real data. Okay, and real performance being delivered. So, with a training set, you train. Why do you need a training set? That's what allows you to get better and better hypotheses. Okay, so taking steps to get better and better hypotheses, but you're searching a bigger and bigger hypothesis set. And then the validation error at some point starts going, and that's basically saying that you're starting to overfit. It can be explained by this picture that we've seen many times. Okay, because you're searching a larger and larger hypothesis set. And by the validation, when the validation starts going up, that tells you when to stop training. So in reality, we train a little bit more, then we see the validation error going up, and we go back to the weights that we had at the optimal number of iterations. Okay, so you have to, in some sense, store, the optimal weights seen so far, optimal with respect to validation error. Okay. And then when you use those weights to classify, look how beautiful the classifier is. Okay, so that's validation, in particular used for early stopping. Okay, so, that concludes our discussion of neural networks. Okay, so, we talked about the derivation of neural networks, about how cascading perceptrons allows us all this power to fit. Okay, then we talked about fitting. Okay, how do you fit the neural network to the data? That was last lecture. And this lecture, we've addressed approximation versus generalization. You have to regularize. Okay, now let's spend a little bit more time on the second issue of the second step in learning with respect to neural networks, which is how to efficiently train, how to efficiently minimize the in-sample error. Okay, so I've erased the board, put up a slide to motivate the discussion. So let's talk a little bit about minimizing the in-sample error. Okay, and this is a huge field it's called optimization. And we are not even going to touch the tip of that iceberg. So there are multiple courses, and you can even do a major in mathematical optimization of various kinds. Okay. Now, first, a quick trick of the trade when you're training your neural network. You're trying to fit the error. Well, so your output node, is h of x is equal to theta of the signal SL, and then so this is what we call XL, and you fit that to the output that you see in the data. Okay. Well, and if you use this as the tan H, well, that's great. It's differentiable. You can run gradient descent, but there's a tendency for gradient descent to get into flat minima, which flat regions which look like minima. For example, there it goes down, then gets flat, then goes down, then gets flat. That's typical behavior when you get into these what are called plateaus. Okay. And that's sometimes caused by the tan H function, because the tan H function becomes flat very quickly. So if you get to large weights, the tan H function is flat, so the gradient is basically zero, and so you don't make any progress. Okay? So, just like we did regression for classification, it's much faster to train regression. You can just remove this theta, and that means that the transform function for the output node is the identity. Okay, and so just like using regression for classification, you can train your neural network as if it's doing regression in order to fit the plus or minus one data. Okay? And that makes training usually faster. So that's a quick trick of the trade, trick of the trade that you should use in practice. Now, when you're done training the neural network for regression, you can put back the tan H and then train a little bit more. And then when you want to classify, you make this the sign. Okay. So that's a quick trick of the trade. Now let's focus on better algorithms. And what you see there is gradient descent in red. And then for as motivation, I'm showing you the queen of algorithms, my opinion, of course, which is conjugate gradient descent. It uses the same information as gradient descent, essentially, which is the gradient. But look how much better it is. And so let's explore a little bit this space between gradient descent and conjugate gradients, and see what kinds of simple enhancements to gradient descent can give us an improved performance. And at the end of the day, I'll tell you a little bit about conjugate gradients, but you can read more about it in the text. And of course, it's a famous algorithm. You don't need me to tell you about it. It's all over the place. Okay. So, what's the fundamental problem with gradient descent? And in general, iterative methods is you take a step at each iteration. And the question is what's the direction of the step? So question one, direction of step. And we have more or less said that it's the negative of the gradient direction. Negative of the gradient. Okay, and then question two, length of step. Okay, and we are using a fixed learning rate parameter. Okay, so we started with normalized gradient descent, which took a fixed step, and then we settled on a gradient descent with a fixed learning rate eta. Okay. And what's the usual problem with fixing anything in an algorithm is that it may not work all the time. So if your error surface is nearly flat, okay, you want to take a big step. If your error surface is very steep, it's too dangerous to take a big step. It'll send you all the way to nowhere. Okay, so you want to take a small step. Okay, but in general, your error surface has both of these kinds of properties. And if you're far away, you want to take big steps. And then as you get closer to the minimum, you want to take smaller and smaller steps. Okay, now, when you start, you initialize the weights. You don't know what your error surface looks like. Okay, so you might start by taking a, whatever default step is. Let's say small. Okay, so the simple enhancement to gradient descent that I'm going to describe is so simple that it is effortless to implement, and it can yield huge benefit. Okay, huge benefit. And so you should implement it. It's called variable learning rate gradient descent. So variable learning rate. Okay, so what is variable learning rate? So you start and you check, did my in-sample error improve? So you started here and you took a step, and so you came here and your in-sample error improved. Okay, so if you improve E in, then eta goes to eta times some factor. Let's call it beta. Beta, for example, could be something like 1.03, 3% increase. So you will increase your next, the learning rate for the next step. So you'll take a bigger step next. Okay, and now you improved again. So you take a bigger step, and now you improved again. So you take a bigger step. Okay, and you take a bigger step. Okay, and now you still improved. Okay, so you take a bigger step. You're getting better and better at this. You take an even bigger step. Okay, because you're increasing. Okay, and now you got much worse. Okay, you got much worse. And so what happens when you get worse? You went from here to here. So if you worsen the in-sample error,
the in-sample error. Okay. Then you shrink eta. Eta goes to eta times some alpha, where alpha is less than 1 now. Typically, we are, relatively conservative in the increasing, because you increase, so you get exponential growth. But when you shrink, you typically only shrink once. And so, we're very aggressive on shrinking. So you might choose alpha something like 0.8. So you really shrink when I increase the error. You can do one more thing. You don't need to stay here. So if you worsen the error, you can always go back. You can backtrack. So what you do is you backtrack and shrink this guy by a large factor, 0.8. So now maybe you'll move to here. Okay? And if you improved, you will increase from here. If you didn't improve, then you will shrink again. And if you didn't improve, you will shrink again and maybe come here. And now you're basically there. Okay? So variable learning rate, it very rapidly adapts the learning rate to your current situation and gets you to the minimum, usually very quickly. So it's a very simple enhancement to gradient descent. You just need to now maintain what's your eta, and you need to check whether you improved. If you improved, get more aggressive. If you got worse, backtrack and shrink eta and shrink it aggressively. Okay. But then, so once we've chosen the direction of the step, which is the negative gradient, you might wonder, well, why do I need to take a step? Why don't I just do line search? Why don't I keep going in that direction until I cannot improve the in-sample error anymore? Okay. And so that's called, gradient descent with line search. Gradient descent with line search. Sometimes I call this steepest descent. But, there's no fixed, well-accepted, terminology for this. Basically, there's no step size. No step size. Interesting. Okay. So let me describe that. Okay. So you don't need to now think about the step. You only tell me the direction. Okay, so you told me to move right. Okay, and I'm going to do a line search. So I'm going to keep moving right until I cannot improve anymore. And boom, in this example, I'm at the minimum. Okay, let me show you. So this is a very trivial example of what's going on in one dimension. Let me show you what's going on, let's say, in 2 dimensions. If you are trying to optimize 2 variables, and in general, we're trying to optimize a large number of variables. The perceptron is d+1 variables, but the neural network can have a large number, sometimes 1 million parameters, 1 million weights. Okay, so what happens with line search in more than 1 dimension? So let me show you line search in 2 dimensions. So line search in 2D. Okay. So you're at some weights. Okay, you're at some weights. Let me call it W at your iteration T. Okay, let's say the minimum is somewhere here. Okay, and for whatever reason, let's say the negative of the gradient. So the negative of the gradient. So let's draw contours of constant in-sample error. So let's draw some contours of constant in-sample error. So this is the optimal. Let me call this W star. Just to show you some of the geometry of, of what's going on. And these kinds of pictures are very important if you decide to go on and study optimization. So the geometry of what's going on is there are contours of constant in-sample error. So I'm drawing them. Okay. And depending on the actual error, okay, these can take on various different shapes. Okay, so now let's say your direction is the negative of the gradient. So can someone tell me where's the negative of the gradient? I'll give you a few seconds. Okay, 1, 2, 3, 4. Okay, and we discussed this, some time ago when we were doing constraint optimization. This is the contour of constant in-sample error. Okay, so the gradient is going to change the error in a maximum way. So that's the direction that changes the gradient the most, that changes the function the most. So it's going to move you as quickly as possible to the next contour. In other words, it's going to move you orthogonally to the current contour that you're at. So the gradient is going to be in this direction somehow. Okay, so where you're perpendicular to the current contour. Okay, so now if you do line search, you keep moving, and as long as you're going to lower and lower contours, you keep moving. So you'll keep moving, blah, blah, blah. Okay, and then once you get to this point, okay, now you see if you keep moving, you're moving to a higher and higher contour. And so this is where the line search will stop you. Okay, so you will move all the way to here. Okay. You will observe something interesting when this happens. So now you're at this point. The new gradient, okay, is in this direction, orthogonal to that. And the direction in which you are moving is tangent to that contour. So the new gradient is going to be tangent to your previous, is going to be orthogonal to your previous direction, and your previous direction will be tangent to the contour that you're currently at, the contour that you have stopped at. So this is just a picture of what's going on when you do line search. Okay. Now, in this two-dimensional situation, we did line search. It doesn't necessarily mean that we have come to the minimum. So now we take another direction, for example, the negative gradient, and we move in that direction, and we'll keep moving until we hit a tangent. We are tangent to another contour, then we move again, and we move again, and so this is line search. Okay. So the philosophy is great, no step, okay, but now we need to implement it. So previously gradient descent, you just compute the gradient, and you move. You compute the gradient, and you move. You compute the gradient, and you move. Okay. So each move is simple. But the gradient computation, especially if you're doing batch gradient descent, can be very costly. So you do all this computation for the gradient and you make one move. Okay. Now, in line search, we sort of do a little bit better. We do one gradient computation, okay, and then we move until we get to the minimum along this direction. So we don't need to compute the gradient anymore. We just need to compute the function. And we would like to get to this point with a small number of function evaluations. We are doing function evaluations to see at every step along this line search, am I at the minimum? Am I at the minimum? Am I at the minimum? So we need to efficiently get here. Otherwise, it's going to be very costly to compute the function many times. And indeed, there's a very efficient algorithm for line search. So let me show you the idea behind that algorithm for line search. So, this is a direction, so you're moving in one dimension now. Once you fix the direction, you're moving in one dimension. So let us imagine that the dimension in which you're moving is this. Okay? And, we're going to move an amount, let's call it eta star. So the function along this dimension looks, we don't know what it looks like, okay? But, let's say it looks, so we're moving in a certain direction, okay? And, let us assume for the moment that the function is decreasing in this dimension, and we want to quickly get to the minimum. Okay, so let's say the function looks something like this, okay, and we want to quickly get to the minimum. Well, we can't take small steps, okay? We're doing line search, okay? So here's what we do. We take a step, okay? Did we decrease? Yes, okay, we decreased. Okay, now double the step. Okay, did we decrease? Yes, we decreased. Okay, now double the step again. Okay, did we decrease? Let's say we doubled the step again, so we got here. So now did we decrease? No. Okay, and so I have come to a situation where I decrease, and then the first time I increase, I have come to a situation which I call a U. So I'm gonna circle this point, I'm gonna circle this point, and I'm gonna circle this point, and you see it's a U. Okay. Once you come to a U, assuming the function is continuous, differentiable, and so on and so forth, we know that once you get a U, there has to be a minimum in this region. Okay, so you what's called bracketed the minimum. You bracketed it in this region. The minimum is between this point and this point. And now you can very efficiently find the minimum by binary search. Okay, for example, now you split this, okay, into two. So you try this point and evaluate the function. And one of two things happens. Either it's going to be lower than this blue point, in which case you've got a new U that's smaller, or it's going to be above this blue point, in which case you've got a new U that's smaller. So you've got a new range. Then you bracket. You halve, and so on. Very fast. So that's binary line search. We can do it very efficiently. So typically in practice, 5 to 10 function calls, and you've got to the minimum. Within some epsilon, within some accuracy. Then you do another line search. And you don't need to make your line search super accurate. Epsilon can be, let's say, 10 to the minus 5. Binary line search converges very fast. Even more efficient. Don't do binary line search. Fit a quadratic to these 3 points and go to the minimum of the quadratic. Oh man, that converges. And now and at that minimum, one of two things happens. Either you're below this guy, in which case you've got a new U, or you're above that guy, in which case you've got a new U. In both cases, you maintain this U, you maintain a bracket for the minimum, and you very rapidly shrink the length of that bracket. Okay? So line search is very efficient. Very efficient. So, let me erase and put on the slide a comparison of these various techniques that we have shown. So far, all these techniques are basically improvements to gradient descent, where the direction in which you move is always the negative gradient. And then, you can take either a fixed step, you can do SGD, or you can do variable learning rate, or you can do line search. Okay. So beefing up gradient descent. It's well worth the little bit of effort it takes. Okay, so in the picture, I'm showing you a comparison of gradient descent with variable learning rate and steepest descent, i.e. gradient descent with line search. Okay. And what we see is that once, line search gets out of the flat region, it takes off and does fantastically. So steepest descent and what we're looking at here is optimization time, not iteration number, because the iterations for steepest descent are more costly than the iterations for gradient descent and variable learning rate, because they just compute a gradient and take a quick step. Okay. Steepest descent computes a gradient and then there's a line search to decide where to move. Okay. In the table, then we can compare steepest descent with stochastic gradient descent, and you see that stochastic gradient descent is slightly better. Okay, and so the current winners are, in some sense, stochastic gradient descent and steepest descent. Okay, and in both of these methods, let me tell you what's the difference. So, you compute a direction, and two, you make a move. Okay, so in stochastic gradient descent, the direction is the negative gradient for a particular data point. Okay, so this is negative gradient for a random data point x little n, and how much you move? A small step. Okay. For steepest descent, it's the negative gradient for E in, so the batch negative gradient, and how much you move? Line search. So you go all the way to the minimum along that direction, so line search. Okay. And so this illustrates that two things. One, you can do quite well by making the most of the gradient that you've computed by going all the way in the direction that you have decided to move in. And stochastic gradient descent suggests that it's not necessarily always optimal to move in the negative gradient for the in-sample error. If you can quickly compute a direction to move, there are other good directions, especially if you can compute them quickly. Okay. So now I'm going to tell you the high-level idea behind conjugate gradient descent, which does use the batch gradient. It's a very good technique, and this is the technique. It's the queen of techniques that uses the gradient. Okay, and I'm going to compare for you conjugate gradient with these three current winners. Okay, for motivation, and then I'll describe at a high level what's going on. And at a high level, what's going on is it's going to say, well, it's not necessarily optimal to move in the negative gradient direction, but we're going to use line search. So whatever direction we choose, we'll use a line search and in some sense make full use of the direction we have chosen. Okay, so here's a comparison on the right between conjugate gradient and steepest descent. And we know that steepest descent is comparable to stochastic gradient descent. And in the table, we're comparing the numbers. And you can see that, okay, if you optimize only for 10 seconds, then the methods are roughly comparable. Conjugate gradient is slightly better than stochastic gradient descent. But, once we move to, 1,000 seconds of optimization, the difference shows up. Conjugate gradient is much better. And then once we move to 50,000, there's no comparison. Conjugate gradient basically gets the error to zero. Okay. And all the other methods are lagging behind in running time, in optimization time. Okay. So you can read more about the details of conjugate gradient in the book, but here's the basic idea of conjugate gradient. So let me go back to this, contours of constant in-sample error to illustrate the idea behind conjugate gradient. I'm going to draw this picture as big as I can without drawing my curves in weird ways. So here's the optimal W star. Okay. And let's say we're at some point W. Let's call this W of t. Okay. And so remember these contours of constant in-sample error. So now let me draw them. Okay. Okay. And they're light, so you can't really see them that well, but they're there. I'm drawing them in red. Okay. Okay, so contours of constant in-sample error. Okay. And so now you remember we choose the first direction. So let's say we're starting the whole conjugate gradient algorithm, and very often in the middle of the algorithm we reset it. So resetting means move in the negative gradient. So we move in the negative gradient. Okay, we move in the negative gradient. Okay, and as we are moving, maybe there's another contour in here. Okay, which is the one we get to for this line search for this iteration. Okay. Okay, so we move, and move. Oh, so much for my abilities to draw curves well. Okay, so we're moving, and let's draw another contour here, which is tangent to that guy. Okay, another contour that's tangent to that guy. So where do we end up? We end up here. Okay. Now, what do we know? What do we know at the point where we've ended up after our line search is that the new gradient is orthogonal. Now that's nice, and I'll tell you what that actually means. That means that the gradient is when you take the dot product, is orthogonal to the direction I moved in. Let me call this direction I moved in, let me call this direction V. Okay, and this is the new gradient, so let me call this direction, this negative, this is G, the negative gradient, so this is G. My next gradient at the point where I stop. And what do I know? I know that G dotted into V is equal to 0. Okay, so let me tell you what that means. That means that I've set, so if you think of an orthogonal basis for my space in which V is one of the vectors, and you can always choose an orthogonal basis with, V as one of the vectors. If V is one of the vectors in my orthogonal basis, then I've set the component of the gradient in the direction of V to 0. Now, if I can succeed in setting the component of G in every basis vector's direction to 0. So if I can get, the components in any basis to 0 for, my D dimensional space, then I've got G equals to 0. And we're going for G equals to 0 because we're going for the minimum. And I've succeeded in getting one of the components to 0. Okay. So now the idea behind conjugate gradients is, well, if you move in this direction, as you move, you're going to change the gradient. Okay, and it's no longer going to be the case that the component in this direction V will be 0. Okay, so the question that conjugate gradients asks is there another direction to move? Okay, is there another direction to move? Okay, so that as I move along this direction, okay, the gradient as I move along this direction, so I can compute the gradient as I move along this direction, and at all times the gradient should stay parallel to the previous gradient. So I don't want the gradient to change in, its direction. Okay, and then when I stop, okay, so here's my new gradient. I know that since it stayed parallel to the previous gradient here where I started, that means that my new gradient is orthogonal to V. And since this is the place where I stopped, okay, my new gradient is orthogonal to this new direction V prime. Okay, and as long as V and V prime are linearly independent, I have succeeded in setting the component of the gradient in two independent directions to 0. Okay, and then I use that same philosophy for the next step. So I have a gradient. Okay. Can I move in a new direction that keeps the gradient parallel to what it was before, but then when I stop, it's now perpendicular to my current direction, and it still remains perpendicular to the previous two, because it's basically parallel to the previous two. Okay, so that's the philosophy behind conjugate gradients, to choose each next direction so that as you move along that direction, okay, the gradient doesn't change. Or more specifically, the dot product of the gradient with respect to the previous direction that you moved in doesn't change. Okay. Now, we can do all the math and figure out what that direction is. And it's a very well-defined direction if the surface is actually quadratic, which means if the surface, which will be the case as you get closer and closer to the optimal. And that's what you see in that picture, that as the error gets lower and lower, the other methods start faltering, but conjugate gradient gets to the minimum very efficiently. Okay. And in fact, it's possible to prove that, if you're in a quadratic error surface, then, it's possible to exactly accomplish all of these. And in exactly these steps, you will have gotten the gradient orthogonal to D linearly independent directions. And so you can prove that conjugate gradient will stop in these steps. Wow, what a beautiful algorithm. In practice, we run conjugate gradient for D steps or maybe D over 2 steps and then restart. And that's because the error surface is not completely quadratic. Okay. And there you see the performance. I mean, the proof is in the pudding. Okay, the proof is in the pudding. It kills stochastic gradient descent. Now, one of the challenges with conjugate gradient, well, you need to compute the gradient and you need to do a line search. And if your data is distributed and so on and so forth, then it's not easy to do these, operations. And that's one of the reasons why stochastic gradient descent is so popular, because data is distributed. And when you're running the algorithm, you just need to go to the server that stores the particular data point you want, compute the gradient, make the move. Okay, it's very efficient. Okay. Now, all the methods that we have discussed only use gradient information. If you're allowed to use Hessian information, then you can do even better. Okay. In fact, the conjugate gradient algorithm for a quadratic surface gets to the optimal in these steps. The second order methods for a quadratic surface gets to the optimal in one step. Okay, so that's the level of improvement from D to 1. Okay, but then you can combine, Hessian information, second order information with line search and do better and better. Okay, so just to show you some of the spectrum of the algorithms that you can implement when you're trying to optimize a neural network. And that's a big deal these days because the neural networks are large and the data sets are huge. Okay? And my recommendation, until you get to the point where data has to absolutely be distributed across, multiple servers, you cannot beat conjugate gradient. That's the queen of the methods. I mean, and there's the proof in the pudding. Okay, we're looking at optimization time. It kills the heck out of stochastic gradient descent. But stochastic gradient descent is a pretty decent algorithm. It's very flexible with respect to parallelization, distributed data, and so on and so forth. So some of the things that people are thinking about these days, from the more algorithmic side, from the point of view of the second step of machine learning, which is to get the in-sample error low. And we are computer scientists. We have to think both about the algorithmic side and the statistical side. The first step, E in versus E out. E in has to be close to E out. Otherwise, there's no point going for low E in. Okay, so that concludes our discussion of neural networks. You've basically seen the entire package, which is why we need neural networks. They are awesome power. Okay, how to fit them, and then how to control them. Okay, and one of the, you can read a little bit about in the text about some of the motivation behind deep networks. How when you use deep networks, okay, each layer sort of has a representation of a feature of the data or of the problem at a different level. So low level features, then higher level features, and so on up to the final highest level feature. Okay, so you can read a little bit about it in the text, in the E chapter. Okay, and of course there are books and books being written about deep learning. Well, I don't have a specific recommendation there, but one recommendation I will give you is stick to the foundations, stick to the fundamentals, and you've seen the whole package. Okay, checking out.